Cool. So the first thing to say, just for the sake of the recording, is exactly what I just said. Namely that this review now appears on the course webpage here. So just look for that. Oh, cool. Anyone else need the notes for the new note packet? Cool. Cool. Otherwise, we happy? All right. So, the first thing to remark is that the first thing we're going to do is just write down a formula that does completing the square. And, as might be expected, at the end of the hour, I was feeling a little bit loose and floppy. So let's just write down the completing the square formula. We'll double check it by foiling out. And then once you have that formula, you'll be able to black box it and just say, well, if I want to complete the square, I could use the techniques we talked about in class, or I could just use this formula. So let's write down the formula. And it is in fact right there. If you want to rewrite ax squared plus bx plus c in the form that looks like a stretched and shifted parabola, you can. The parameter of big A is the same as little a. The parameter of big B is 2b over 2a, little a's. And big C, which is circled here because it was the one that was giving issues, is little c minus b squared over 4a. And if we want to check that, we can just check it. So let's check the completing the square formula. And completing the square formula says that ax squared plus bx plus c is the same thing as big A is little a. X plus big B is 2b over 2a squared plus little c minus little b squared over 4a. So the completing the square formula says that that equation holds. Let's check it.
Is that 2b over 2a, or is it just 1?
Right here, just b over 2a.
Okay.
There should only be 2 in the denominator. In fact, if it were 2b over 2a, then I should simplify it, right? Why am I using a non-erasable pen? All right, so there's some identity that I claim is true. If you want to convince yourself that an identity is true, well, one way to do it is just take the more complicated looking side and simplify it. Does one side of that look more complicated than the other? Yeah, so let's just simplify that side. So, if I were to ask you in the wild to simplify this, what would you do? Well, there's an obvious, complicated looking bit. There's the squared bit. How does that simplify? What does that mean? But the what I'm fishing for is you need to FOIL it out, right? So I would like to know, what is this? Well, what is it? It's a times x plus b over 2a times x plus b over 2a plus c minus b squared over 4a. Right, all that squaring means is multiply it by itself. So, how do you expand out this product? What do you need to do? Multiply the first terms together, then the outside terms, then the inside terms, then the last terms together, and add them up? Yeah, so let's do that. Leave the a alone. First term, x squared
outside plus x times b over 2a plus inside. So that's this one. Inside b over 2ax plus last.
Fraction multiplied by itself. Multiplying fractions is easy. You just multiply the numerators and multiply the denominators. It's addition that's hard with fractions.
B squared over 2 times 2 is 4a squared plus c minus b squared over 4a.
All right, I just want to simplify. So what do you see that simplifies there? Is there maybe a term in that sum that you see added to itself? Cool, yeah, so let's take advantage of that. Thing plus thing is just 2 times thing.
2 times x times b over 2a
All right, so remember the eventual goal is I want to simplify that down to just ax squared plus bx plus c to make sure that this completing the square formula is correct. What would you like to do to that thing next? Yeah.
Should do that.
Yeah, great. That seems wonderfully useful. Let's do it.
ax squared plus 2ax b over 2a. Make those x's squiggly so I don't think they're multiplication, plus a times b squared over 4a squared plus c minus b squared over 4a. And one thing I see there that makes me happy,
I like that. I like that ax squared because I want to see an ax squared. All right, what next? Like the bits that have division look complicated, right? And whenever you see something multiplied and then you divide by that same something, you can cancel. So let's look at these complicated bits.
do you see any cancellation there?
Is there anything in the numerator and in the denominator?
The 2A.
2a. Multiply by 2a and then you divide by 2a.
Those will cancel. How about this piece?
Yeah. Yeah. The a will cancel with one of the a's in the a squared.
All right, so let's carry on. So what do I wind up with? I see a x squared b times x. Right now it's xb, but it could be bx. Plus b squared over 4a plus c minus b squared over 4a.
Yeah.
Oh, yeah, absolutely. Sorry about that.
If you have any urgent texting you need to do on that phone, just ask you to step outside. Okay, we're fine.
All right, anything that cancels? Yeah, there's something that you add and then subtract. All b squared over 4ac minus b squared over 4ac. I don't care what b squared over 4ac is, it cancels because you add and subtract it. Oh, cool, and I'm left with ax squared plus bx plus c, which is what I thought I should get. There's why the completing the square formula is correct. There's nothing magical about it. If you just FOIL out the square side, you'll get ax squared plus bx plus c. And it's always nice to like see why a mathematical formula is correct. It's just algebra. And if you want to continue on that vein, then extra credit that follows this immediately will have you use the completing the square formula. So the formula that we just wrote down is all you need to show that the quadratic formula is true. It's where it comes from. But instead of that, I'm going to use completing the square for something a little bit different. And let's start with a quick story for motivation. So, how many people here have read the short story by Leo Tolstoy, How Much Land Does a Man Require? Well, I guess like the English translation. All right, cool. It's all worth reading. I'll give you the quick synopsis. So the premise of the story is the protagonist Paco is born poor, doesn't have anything. Makes a deal with the devil. Says, devil, if you acquire me riches and land, I will sell you my soul. Devil says, sure, great, sounds like a bargain. So he goes about his life, he acquires land, and becomes quite the miser. Takes stuff, gets rich. And he learns about an interesting proposition that a village in the area is offering. If you go out to this village, and you give them some amount of money, then they will let you walk for the course of one day. And along the way, you'll plant some little flags to indicate where you walked. However much land you enclose, you will receive. That will be your land. If you don't make it back and close up your loop before the end of the day, you'd get nothing. He says, great, I can manage that. And so he starts his walk, and really is ambitious. He goes out far and wants to get lots of land. And then he notices that the sun is setting, so he has to make it back. So he hurries back. He really runs. Makes it to his endpoint, back to the village. The villagers cheer on his good luck, nicely done. He makes it back to the village and immediately dies of a combination of exposure and exhaustion. With the closing line of the story being, and so we see how much land a man requires is about 6 foot by 2 foot. It's a walk across the torture, so you expect it to be dark and in no way uplifting. Anyway, so I encourage you to read that story at some point. It's in the public domain. There's a link there to the Gutenberg Project. In fact, there's a QR code there to the Gutenberg Project. Maybe people have found the Gutenberg Project at some point. Yeah, stuff in the public domain they just put up. Right there. They also have audiobooks that aren't necessarily well read, but they're free. Neato. Optimism. So here is the variation I will take on that. Instead of asking the question, how much land does a man acquire, I will ask the question, how much land can this man acquire without dying? So, let's do that. Let's ask this question. We will use the theory of optimization of quadratic functions to save Paco's life. And we'll make some simplifying assumptions. Let's suppose that Paco is quite confident that from sunup to sundown he can cover 40 miles. That doesn't actually seem that ambitious. That seems quite reasonable. And this is a made-up example, so your mileage may vary. Change the number if you think you could walk farther. So let's understand the question. Paco is going to walk in a rectangle of total perimeter 40 miles. He wants to capture as much land as possible. He wants to maximize the area. So we're going to try to write down some function that spits out as its output area, and its input will be some decision that Paco needs to make. So let's try to walk out what that is. So let's maybe draw a rectangle. So this rectangle, it has length x, he'll go x miles east and west. It'll have height y, y will be how far north-south he goes. And so right now it looks like you need to choose both x and y.
And there is a theory of multivariable optimization, but it's a little bit more complicated than I want to use here. I'd like to get down to like one variable worth of stuff, but there's a relationship that x and y have to satisfy, right? What's the perimeter of the rectangle I would like? 40 miles. Is there a formula for the perimeter of that rectangle?
2x plus 2y.
Nice. There's an equation. That's a constraint. 2x plus 2y. That looks like something you could either solve for x or solve for y. And just in order to go with the flow of the paper, I'll say solve that for y. What do you get? So, what is y?
We got 20 minus x.
20 minus x. Do I hear a second? Do I hear a call to go through the algebra? Cool. Awesome. So, that means that Pacom only needs to choose x. Once he does, the choice for y will have to be 20 minus 2. 20 minus just 1x. 20 minus x. And I want to maximize area, so maybe an area formula would be nice too. What's the area of a rectangle? X times y. So the area, the thing I want to maximize, is x times y, and I know what y is. That'll be x times 20 minus x. And that's nice. So now I'm down to the desire to maximize that thing. And here's the strategy I'll follow. If I could graph that, then I could read off the maximum value from the graph. So let's just try to sketch the graph. And how do you do that? Well, you need to complete the square. Before I complete the square, I think I want to put it in standard form first. So let's take that and like expand it out. So let's go ahead and do that. Expand that out. That is, well, I guess you need to distribute 20x minus x squared. I want the x squared term to come first just to make it look in a form that won't confuse me. If you don't need to do this step, then don't do this step. Gesundheit. Minus x squared plus 20x. All right. So, from that immediately, I can't read off what the maximum is. Well, I will be able to once I get a formula that'll show up on the next page, but I want to do it without that formula for now. Can you put it into this form? Yeah. We have it in this form, we'd like to put it in that form. What's the a that we have in this problem? -1. So I'll even jot those down. A is -1. What's b?
20.
C? 0. All right, you can throw a plus 0 at the end of that. So, by completing the square, this is the same thing as a is -1, so negative x plus b over 2a, 20 over 2a, so -2, squared, plus c, so 0, minus b squared over 4a. Negative b squared, so 20 squared
over 4 times -1, so -4.
Cool. So the completing the square formula we can just use. We know why it's true now. I guess we should simplify that. 20 over -2 is -10. Yeah.
So, negative x minus 10 squared plus,
Let's see, 20 squared is 400, but then I need to divide by 4, so that's 100. And there's like a double negative there, so those two negative signs will cancel. Oh, neat. Is that now something that's easy to graph? Yeah, so you'd start with like an upward opening parabola. And then because of the minus sign, you'd flip it upside down. And then you'll shift it 10 to the right and 100 up. So it'll be like a downward opening parabola whose vortex is at 10, 100. Nice.
so if here I see a graph whose y component is the area of the resulting rectangle and whose x coordinate is the length that we called x. That's why I didn't want you to solve for x and have y as the variable and then have the x-axis be the variable called y. It wouldn't hold anything, it'd just be confusing. We see this point up here at 10, 100, and then it's a downward opening parabola. And I won't check the intercepts, but one of the intercepts will be at 0, 0. And it'll be over there at something else.
Cool. So, now let's look at that graph. What is the maximum value this area function takes? That's the input value. Yeah. So maybe you're answering the questions in the order listed instead of the order I was asking. The maximum area is 100, and maybe we should put units. What are the units on this area? Miles, but square miles because it's a unit of area. 100 square miles. What's the length of this ideal rectangle? So that's like the x variable. 10. I'll put units in because those kind of matter. What about the parameter called y? Could we figure that out too?
It would also be
Right.
just putting the x value.
Cool. Yeah, so if we know the x value, then, well, earlier we established what y is as a function of x. So that y value is 20 minus x is 20 minus 10 is 10. 10 miles. And so the maximum area, now we can even double check, 10 miles by 10 miles is 100 square miles.
Cool. So how do you feel about that application? So if you want to maximize or minimize, if you want to optimize a degree 2 polynomial, completing the square is super useful because if you complete the square, then you can just say what the graph looks like. It'll look like a parabola. Maybe it'll be flipped over, maybe it'll be stretched, and then it'll be shifted. And how far you shift will tell you where that turning point is. That turning point gives you the maximum or the minimum if it opens up. Groovy. So, what I'm going to do on the next page is just going to take the same idea. I'm going to abstract some of it away so that you don't have to do all of the computation every time. I'm going to extract some more formulas that will just come from completing the square. So let's do that. So, this page is going to wax a little bit abstract. The key result will be this theorem down here. But let's try to establish that result first. So, since this is all going to use completing the square, let's write down the completing the square formula. If f of x is ax squared plus bx plus c, then the result of completing the square will be a times x plus b
over 2a quantity squared plus c minus b squared over 4a.
And that completing the square formula, if you wind up using that formula a bunch for all the completing the square problems I'm going to give you, then you'll wind up memorizing it anyway. And if you prefer to just complete the square using one of the ad hoc techniques, then you don't need that formula. But I'll use that formula just so I don't have to do the hard work. Let's think about what the graph would then look like. So the resulting graph is a parabola which opens up or down. And I think the answer will depend on whether A is positive or negative. So if A is positive, tell me about the resulting parabola. Upward opening or downward opening? Upward opening, because you won't do a vertical flip. It will open up when A is positive. What if A is negative?
It'll open downward.
It'll open down, because there will be like a vertical flip.
The color coding is nice. Next. Ooh, that's a silly typo. Let's think about how it's shifted. So you'll take a parabola. Depending on what that A is, maybe you do a stretch, maybe you do a compression, maybe you do a flip. That plus B over 2A, what will that do to the graph? Imagine that plus B over 2A were just a 5. What would it do to the graph?
To the left.
Move it to the left. By 5 units. Oh, yeah. Yeah, sorry, I struggle with that. My left isn't the same as your left because I'm looking at you. You know what left means, though. So what will this do? This will move the vortex left by B over 2A, and it'll go up by this much. Or down if it's negative, but you know that. So let's draw a cartoon graph. So summarizing this, if A is positive, then ax squared plus bx plus c looks like there's some vortex here at coordinates, you go left, so negative b over 2a, and then you go up by c minus b squared over 4a. I should make it clear that only the b squared is divided by 4a. And the parabola opens upward. Similarly, if A is negative, then the point is the exact same. This point will be at negative b over 2a, comma, c minus b squared over 4a. And I've drawn that vortex point like it's in quadrant 4. Does it have to be in quadrant 4? Is there like a guarantee it will be? No, because I don't know whether b over 2a is positive or negative. I don't know whether the y-coordinate there is positive or negative. So let's read things off. This function, does it have a global maximum or a global minimum? Global minimum. There is a least y value you see. What is the x value that produces that global minimum? That x value. Similarly, if A is negative, this thing opens downward, so I see a global maximum at x equals negative b over 2a. So here's the payoff. If I just give you a degree 2 polynomial, 3x squared plus 5x minus 7, well, that 3 is positive, so you know it'll have a global minimum. And you know the x value that'll produce the global minimum, it'll be negative b over 2a. I forget what all of the a, b, and c were at this point, but it'll be whatever that fraction is. And so now you can just black box that. If you can just remember negative b over 2a is the address of the vortex, then you can maximize automatically a degree 2 polynomial. And so maybe I'll just write that down.
the quadratic function f of x equal to ax squared plus bx plus c has a vortex at x equals negative b over 2a. Could we also write down the y-coordinate of that vortex point? We could, and I guess I will. The reason I don't have it here is because, well, you can also just always figure out the y value if you know the x value by plugging it in. So I'll put it down, but I don't regard it as important. Y equals c minus b squared over 4a. When a is positive, the vortex minimizes. When a is negative, the vortex maximizes. And you'll notice that that's when a is positive and when a is negative. There's a number that's not positive and not negative, 0. What would you do if a was 0?
It would be all real numbers, right? Maybe I understand.
Well, what would be all real numbers?
The graph, like there would be no minimum or maximum, it would be all numbers that can be in the graph.
Yeah, so there's no minimum or maximum because it hits everything, because it'd just be a line, right?
Yeah.
Yeah. So you shouldn't use the vortex formula or talk about the vortex at all when you have a line. Cool. So I don't know, like, that seems like a reasonably handy formula to keep in your head. Whenever you want to optimize, remember the vortex formula. The vortex formula says that this turning point of a parabola is at the coordinate x equals negative b over 2a. And let's use this now. So this concludes the technical sounding page of this set of notes. What I want to do now is let's just apply this to some applications. And yeah, we're actually doing pretty good for that. So I think maybe this one I want you to make an attempt on. So here's a setup. In order to keep away prying eyes, you have a secret you want to keep. So you're going to build a fenced off area, one side of which is adjacent to a cliff face. So you can trust this cliff face, which is really, really tall, to keep unwanted visitors out. You've secured 1,000 feet of fencing, and you're going to enclose a rectangular region with this 1,000 feet of fencing. The bigger the area is, the more reliably you'll be able to keep your secret, because it'll just be buried somewhere. How much area could you enclose? What's the maximum area you could enclose? See, I see people seeming to make a decent start. Is there anyone who's unsure how to get started and wants me to say some words just to get things started? Cool, then I will. So, you have these 1,000 feet of fencing, right? So 1,000 feet is equal to total amount of fence. Well, it looks like in this diagram, there are only 3 sides you need to fence. The other side is the cliff wall. So I think maybe assign variable names to those sides. Then we'll write down an equation. I think the top side and bottom side are equal because they're both, it's a rectangle. So you've got 1,000 feet of fencing. If you pick side lengths x and y in that diagram, then how much fence have you used? How many x's?
2,
How many y's?
1.
So in total, 2x plus y. And I won't address this. I'll leave that to you. Because does that look easy to solve for either x or y? Does it look easier to solve for one than the other? If so, then that's the one you should solve for. We want to maximize the area of this rectangle. What's the formula for the area of this rectangle?
What's the formula for the area of a rectangle of side length x and y? Cool. So, here's the strategy. That looks like you could solve that for x or y, take your pick. Take whatever you get, plug it into this. Now you'll have a degree 2 polynomial equation, degree 2 polynomial function, a quadratic function. You want to maximize or minimize, maximize, I guess. So I guess take what you've got written down, make sure it has a maximum. It probably does, because probably you can't like enclose an unlimited amount of area inside of 1,000 feet of fence. That would be weird. So you want to maximize. Vortex probably maximizes, find the vortex. Those seem like ideas? During this process, you can be collaborating with each other. Even if it's just to check your answers to the various steps against other people.
So once we have the area form, what we did in the last. So the area would be x times negative 500, because that's what
There's only one line.
Okay, so it would be.
So it's equal. I forgot.
Cool. What do you think? Should we come together? Yeah, so let's start with this. We've got the 1,000 feet of fencing, so that's the amount of fencing you're going to use. If you make the choice x and y as in that diagram, you'll use 2x plus y. I guess the units should be feet of fencing. So those two better be equal. What do you think? Should we solve for x or solve for y? Which seems easier? Sure, we can solve for x. So solving for x, I guess we'll need to subtract y to the other side. 1,000 minus y equals 2x. So 1,000 minus y, then divide by 2 is x. That's what you get if you solve for x, and we can use that. How many people solved for y instead? Cool. And you just have to do one or the other. You definitely don't have to do both. So maybe I'll pose this as the alternative one where you solve for x instead, for y instead. What do you get if you solve for y?
One y equals 1,000 minus 2x.
1,000 less 2x. Cool. And I'll just hang on to both of those. You only need to get one of them. If that's all you need to go on to the next step. So let's use that. So I have a formula for x in terms of y. So let's use that to get a formula for the area. So the area is x times y. So it'll be 1,000 minus y over 2 multiplied by y. If you solve for y instead of solving for x. I'd like to turn that into something that looks like a standard quadratic so I can use the vortex formula. So I guess that means I need to do some distribute that division and then distribute the multiplication by y. That seems in line with what people did. So let's do that. 1,000 divided by 2 is 500. 500 y minus y squared, but there's a 1/2 next to it. Cool. That feel pretty good? Is that in the needed form? Yeah, the variable is y instead of x, but who cares? The coefficient in front of the variable is negative, so does the vortex maximize or minimize? It would maximize? So I guess the graph here, it would be confusing to draw because there would be a y-axis and an area axis. And this says it'll open downward like that, so it'll maximize. And I'm going to split this into two for the two different ways we could do that. So the vortex is at y, because y is the variable right now, equals negative b over 2a. And what is the value of y that we have? Well, no, let's do that. So what is b right now? Yeah, say it louder then. 500? So it'll be negative 500 divided by 2 times, what is a?
Negative.
Negative 1/2. What's that simplify to? I think just plus 500. There's a double negative going on. There's multiplication by 2 and then division by 2. Cool. So that tells us the value for y that will result in the optimal choice of area. And now, yeah. Oh, yeah, I'm sorry. There we go. And I think I even have everything that I need on camera right now. Let's also, how many people solved for y instead of solving for x? Cool. Let's go through that same wall and see what happens. Nice. I don't know if I'll ever get that pen back. If you solve for y, you get 1,000 minus x, and so you'll get area equals x times 1,000 minus 2x. And if you distribute and switch the order, I guess you get something like negative 2x squared plus 1,000x. Is that right? Yeah.
So once you do find the x value, which equation would you plug it back into? Would you plug it into the area equation or the y equation to find the y?
If you want to find y?
Yeah, if you already have x, which of the two equations do you plug it in?
Yeah, so if you already have x, it depends on what you want. If you want the area, then you should use the formula for area.
Okay,
If you want y, then you should use the formula for y.
okay.
So the answer is both, because I think the problem is going to require both things. So let's plug along. That parabola, will it be upward opening or downward opening? Down, so the vortex maximizes or minimizes? Awesome, maximizes. So let's just write down where the vortex is. So this will have vortex is at x equals negative b over 2a. And if you plug in the choice for b and a as appropriate, what do you wind up with? Yeah.
What is a whistling sound?
What's the whistling
Are
sound?
you hearing that too? There's like some type of whistling sound's been going on the whole class. I'm just making sure I'm not insane.
Yeah, I heard it too.
Okay.
It's like on the back of the class, just be cognizant of it, you'll probably hear it. Just owl. That's what I'm wondering.
I think this is like I'm not doubting it's there. I'm not hearing it.
Okay.
I think this is one of these things. I've been told this.
Yeah.
Oh, it's gone now?
No, just there goes again.
Yeah.
I'm losing my mind, sorry.
No, you're not, because everyone else is hearing it other than me. Are you hearing it?
Yeah. He's
Okay, that's
sharing his hallucination.
Yeah, I don't know what to do about it. 'Cause
No,
I'm
that's
sorry about this.
making sure I wasn't going insane.
No, you're apparently not. If anyone, I am, because everyone else is hearing it. Cool. So if you use the vortex formula now, what do you get for the x value? Well, it'll be like negative b over 2a, right? So negative 1,000, because that's b, over 2 times negative 2. Is that 250? Does that agree with what other people got? Cool. So the vortex is at x equals 250. And we've done something like really inefficient here, so like, because like we did the problem 2 different ways at the same time. So on one hand, we now know the x value and we know the y value. Ideally, you wouldn't have done that this way. You would have found the x value. Once you know the x value, how would you find the y value? Do we have something that says what y is if you know x? Yeah. There. So y is equal to 1,000 minus 2 times 250. That's 500. That's good. That agrees with what the other formula gave us. So let's now make sure we're answering the whole question. How large an area can you capture? Have we answered that question yet? No, but like we basically have, right? How much area have we captured? Whatever x times y is, right? So the max area is x times y is 500 multiplied by 250. I think that's 125,000. Oh, sure, yeah. So the max area is x times y, so we just need to multiply x by y. 500 times 250 is a great answer to this question, but it is the same thing as 125,000. Oh, units, what are the units on this area? Square feet, because it's units of area. Nice. Groovy. So, there's one page left in this particular pack, and we'll go through it on Monday only by demand. So take a look at this optimization problem. And answer. With the observation that there's a silliness about inconsistent units that you have to deal with before you even begin. So take a look at that. We'll go through this page next time if people want. Yeah, sorry about the whistling.
No, it's okay, I was just making sure I was going crazy.
Yeah, not really.
Where, I mean, I was catching my.
Oh, yeah, no, I don't have one to back anything.
Okay.
That was it, so.
See if I can do it.
Really, that's.
I think, I heard it after you brought it up, I think it's Pelican.
I think it's the doors opening and closing underneath the stairwell. Because we're above the stairwell.
Oh, okay, it would make sense how I would have had that toned out. Okay. Okay.
Are you get on tomorrow?
Yep, my 1 o'clock office hour.
Okay. Because I can help with the one today.
Okay. If you have time, you want to like compose an email like trying to phrase the question, I'll try to take a look beforehand. And you really take the effort to composing the problem, and what might be that's your problem. That sometimes.
Like ask questions.
Okay. All right. Yeah, I'll see you at drawing office hour then.